Hello, everyone. Welcome back to Daily Coding. Today's day 45. I'm in a bit of a rush today. I have a little less than 30 minutes. So let's try another greedy problem. I'll look at this one. I haven't really looked at it yet. Okay, so I forgot to open Paint. You are given an integer. 1 second. You are given an integer array nums where each element nums of I indicates your maximum jump length at that position. Return true if you can jump to the last index starting at 0 or false otherwise. Okay, this one's true. First jump from index 0 to index 1, and then to index 3, 1, 2, and then 1 from index 3 to index 4. So we have to get to the last index. Okay. So okay, so do we start on index 0? Okay, so we have to jump at index 0, right? Is this not... If you have to start at index 0, then don't you just jump there and just kind of follow the path? Oh, maximum jump length. Okay, maximum jump. So, okay, so our decision tree would be like, we start at position 0, and then we branch, let's say like j times, where j is the number to jump. So like if it's 1, then we only have one path. If it's 2, then we can either stop at 1 or stop at 2. If it's n, then we can do all of that. And we just repeat that process. So I'm trying to think when would be a good idea not to do your max jump. Well, I guess if you had 2, 4, 1, 0, and let's say like 4 gives you to the end, 1, 2, 3, 4, like this. So in this case, when you start here, you don't want to take your max jump. You want to take this one. And then I can think of another example. So if you have 2, okay. Another example would be if you had like 2, 2, 1, 0. Okay, this could also be 3, 1, 0. So we could have this, and this would give you... So I was going to say this could give you out of bounds, but if you're ever out of bounds, then that means you can just jump to the end. You can always jump to the end. So is there ever a situation where we want to pick the... So, okay, so here we look at all of our numbers, and then we just like pick the biggest number. Is there ever a situation where you wouldn't want to just pick the biggest number? Or maybe that's what's greedy about it. Okay, let's look at the test cases here. So 1, 2, 1, 0, 1. Okay, so we start here. We only have one option. So we look here and pick the biggest number here. That's 2. Okay, then we're here. Now we look at these two, pick the biggest number there. Whoops. 0. I was doing the wrong test case. Okay, we look at these two, pick the biggest number out of those, which is this, and then we get to the end. Okay, and then if we look at the other one, 1, 2, 1, 0, 1. We start here, pick the biggest number here, and now we pick the biggest number here, which is 1, and then we can't jump there. Okay, so if it's 1, 1, we want to pick, like, so for instance, if we had 3, 1, 1, 1, 0, I guess it doesn't matter which one we pick, but the most efficient one would be to pick this one. Okay, so let's think about it more like mathematically. So if we have a 3, let's say, and then a 6, so this 3 can reach, so let's color coordinate them. So 3 can reach 1, 2, 3. Then if we have a 6, it can reach 1, 2, and then 4 more also. So it's like, this is basically just a better choice because it can do everything that 3 can do. And then if we had, let's say, a 3 here and a 2 here, so now it's the same, so it doesn't really matter which one you pick. They have access to the same places. If it's a 4 here, okay, so now this is a little interesting. So what if a 3 is here, but a 2 is here? So the 2 is better in this case, but what if you're selecting, like, what if the biggest number you found so far is you're at position right here and you have 3? So you can either pick, so normally with the current algorithm, what I do is look at these and pick the largest. Maybe what we want to do is for every number calculate the max index it can reach. So for instance, if we index these, we have 0, 1, 2, 3, 4, 5. So we say, okay, this can reach 1 plus 3 is 4. So it can reach up to index 4. We don't have anything here. So we'd calculate that one, and then we calculate this one. We say, okay, this is 3 plus 2. So I'm doing index plus value equals 5. So because this is a higher value, it can go further. We'll pick this one. And then, like, let's say it was bad because there was like 7 here or something. Well, we would say, okay, 2 plus 7 equals 9. So this can reach the furthest. So we would just do that. So this would be worst case scenario. I feel that this would be n squared because if you have a bunch of 1s, let's say, so this one, well, actually this would be n because each one, the subarray length is only like 1. So this would be n actually. It could be 0 as well. So if you have a bunch of zeros, then you would just say, if you're at a 0, that means you lose basically. So hopefully, yeah, we'll get there. Okay, so I'm gonna try. So I have 20 minutes. So I'm gonna try to code this idea. Okay, so we'll start with current jump equals nums of 0. So we start at index 0. And then what we want to say is, so we want to find the best position. So we'll say for I in range, so whatever index we're currently at, and then current index plus, so this will like scan for new, so scan for place to jump to. Okay, so from our current index, which is always going to start as 0, and then to our current jump value. So for instance, let's say our first jump is 3. We just delete all that. Okay, so if our first jump is 3, let's say 2, and let's index it 1, 2, 3, 4, 5. I'm just deciding whether or not I need +1 here. So it would be 0 plus 2. Yeah, so we want to do index 0, index 1, so we do need the +1. All right, and let me just print. Okay, so then what we want to do is max potential equals infinity. Okay, and then we'll say, all right, if I plus nums of I, so that's like the potential score. So if we had a 6 here, we would say this can get us to position 2 plus 6, which is 8. So if this is greater than max potential, then we'll say if it's greater than, well, first of all, I guess we could say if I plus nums of I is greater than or equal to the length of nums. So this would be our stop condition. So if this number gets us to the end or past it, so the last index, so do I have to say -1? No, I think, so if it gets us to index 4, which is the length, -1. Okay, so if it's greater than or equal to the length, then we return true. So this is like we won. Otherwise, if it's greater than max potential, then we'll say max potential equals I plus nums of I. Current index, well, I guess we could say max potential index equals I. Okay, so I is like something we're jumping to. So from where we currently are to the range of everything we can jump to. So if this number that we're at plus its value is greater than the length or equal to the length -1, then that means it's possible. Otherwise, the general case, if that number we can jump to plus its index is greater than the current one we've seen so far, then we redo max potential. And then we keep going until what? What's our stop condition? Until we can't move anymore. So until we reach a 0, I think. So I guess we could say while max potential does not equal 0. Because otherwise we'll always be able to move. So if our max potential is 0, well, I guess we want the number. So this is kind of strange, but if max potential value, this, yeah. And then if it does equal 0, we can return false. Okay, so let's see what errors this gives us. We got 15 minutes. Max potential value equals -1, doesn't matter. Infinite loop. Okay, let's say, let me just show 5 iterations and count as less. Oh, I'm never setting, yeah, so I have to say current index equals max potential index, and current jump equals max potential value. Okay. All right, this might be worth it. So here we're at a 0. So basically the 0 gets checked. So here we can return I'll just say if length of nums equals 1, return true. Okay. Alright, so we got it. I honestly have no idea if that's how I'm supposed to do it or not. The runtime is a bit confusing because we're always jumping, but it seems good. And then we don't need this part. So let me just see what we really need here. Max potential, we don't need that variable, do we? I guess we do. We don't need count. Okay, while we can keep jumping. So is there a better way I can define this? So I have these 3 variables basically. And I don't want to assign them here because you don't want to mess with the for loop. Honestly, I mean, maybe it's fine. So obviously our max potential can be defined as max potential val plus max potential index. Maybe I can make it a tuple, actually. Maybe that would make more sense. So if I said max potential equals, so we want the index and I and nums of I, like that. And then if we say it's greater than max potential of 0 plus can you sum a tuple? Let's try it. 3, 6. Print the sum of A. I don't know if you could do this. Let's see. Yeah, you can sum the tuple. Okay. So instead here, I'll just say the sum of max potential. And here we'll say current. So current will be equal to a tuple. Or actually, so we'll say max potential equals 0 and nums of 0. Like this. And then we'll say current equals max. Is there a better variable name than current? current of 0. Well, yeah, the index is 0. So current of 0 till sum of current plus 1. This part is off. So what am I trying to do? I feel like it could be this point. Okay, so let's think about it. So here we have max potential, which is an index and its value. So we initialize it while it doesn't equal 0. So while the value does not equal 0, current equals max potential. Okay, so then we go from the index until their potential plus 1. I don't know if this should be sum. But I have it as sum though. Yeah, actually that makes sense. So this works. This part is off. So I had it as if it's greater than negative infinity. So I think we just say here it's max potential of 1. Yeah, this is the problem. So I also got to set it to negative infinity. Yeah, maybe it's just more complicated this way. So I'll just stick with this, with the variables. And then just get rid of count. Alright, yeah, so thank you guys for watching. This was Jump Game.